Hey y'all, I hope you're having a good day, and today I'm going to talk about quantum mechanics in a nutshell, and this is part 2 to go along with part 1, which I already made a video on. And in part 1 I talked about states and probabilities and the Schrödinger equation, and I said any general state, I called it psi, could be written as a linear combination of basis states, which I called phi. And if you take the coefficient in front of the basis states in the linear combination, and you take the square of it, or modulus, well then that's the probability that you find your system in that state. And I said that states evolve in time according to the Schrödinger equation. So that was all about states. Now part 2 is going to be all about operators, and I'll also talk about average values and Dirac notation. So, in classical mechanics, we have quantities such as energy, momentum, and position. Our energy we would usually write as the sum of the kinetic energy plus the potential energy. Or you could write half times the mass times the velocity squared plus the potential energy. So your kinetic energy is always going to be this for one particle, but your potential energy is going to vary whether depending on what field you're in. If you're in a gravitational field, you'll have that gravitational potential energy right there. If you're experiencing an electric field, then you're going to have the Coulomb potential energy in there. And the momentum is usually written with a P, and it's the mass times the velocity. Or you could also write it as mass times the time derivative of your position. So if we were to call it to position x, well, we could also write the velocity as dx dt. Okay, so in quantum mechanics, things are a little bit more weird. Instead of talking about these quantities that are continuous in classical mechanics, in quantum mechanics we call these observables. And we use operators. So if we want to talk about the energy, well, any quantity we want to talk about, we just put a hat over it, and it becomes an operator, and now it's quantum mechanical. And quantum mechanical operators have certain properties, such as their Hermitian. I'll talk about what that means later. So if we want to write energy, the energy operator is the Hamiltonian, and you can write that as the kinetic energy operator plus the potential energy operator if you want. And this is going to be different depending on what system you're considering. The momentum, we write p hat. See, all we're doing is putting a hat over this. But in quantum, it's a lot different with momentum. We would write negative IH bar dx, or more generally, if you're working in more than one coordinate, you could just write the gradient. And the position is the easiest one, it's x hat. And there's also some more, such as angular momentum operators and spin operators, but this is just quantum mechanics in a nutshell, so I am not going to talk about those here. So, if you've taken a course on linear algebra, then you've probably encountered operators before. For instance, if I have an xy plane and I transform the xy plane, the transformation comes about through an operator. Let's say I got two basis vectors, x hat and y hat, and I'm going to call x hat 1, 0 and y hat 0, 1. Now let's say I transform my coordinate system by rotating it 45 degrees. So this x hat is going to rotate to here, and this angle is 45 degrees here. And let's call this x prime. And over here is going to be the moved y hat. Let's call that y prime. And now if you remember back to your linear algebra, the rotation operator can be written down as a matrix. And the matrix elements are cosine theta, negative sine theta, and cosine theta. So what you're doing when you're rotating your whole coordinate system is you're operating on each and every vector in your space with this rotation operator. So for instance, let's operate on our x hat vector. So if we go through the math and do our matrix multiplication, we find out that our operator operated on our vector and produced a new vector, and the new vector is root 2 over 2 and root 2 over 2 are the elements. And that's exactly where we would expect to find this x prime. And you can do the same thing with y prime. You're just going to get, so y prime would be negative root 2 over 2 and then root 2 over 2, because you're going minus root 2 over 2 this way and up root 2 over 2. So that's how I like to think about quantum mechanical operators, is as matrices performing a transformation on a state. Now let's talk about the average value of any operator. Let's take the general operator A, okay? The average value of A we would write as such. So we sandwich our operator between our two states. And these states could possibly be different, so I'll denote them sub I and sub j. And remember that the one on the left side of the operator is, you have to take the complex conjugate of it. So this is the average value of our observable A. Okay, so now that's the definition of average value. You may also see average value as written like this. And this means the same exact thing as this, but this is written in Dirac or bracket notation. So let's go into this Dirac notation a little bit more, because I find it easier to work with than thinking about these integrals. So we have three different parts in our Dirac notation we've written down here. We have this part, and this part is called the ket. So psi j, this is called the ket. And you can think of it as a column vector. Now this one here, we would write like this, and this is called the bra. And we can think about this as a row vector. Okay? And this part in the middle here is just our operator, right? A. And it's just called the operator. And it is represented by a matrix. So what you're doing here is you're multiplying a column vector by a matrix, which is going to give you a new column vector. And if you multiply a row vector by that column vector, you're going to get a number. So anytime you see closed brackets here, by closed brackets I mean the points point outward, that's going to give you a number. So doesn't matter what's on the inside, that's going to give you a number. But let's take another case. What if we have psi j over here, and it looks like this? And let's just write psi I over here. Well, this is the brackets aren't closed, so this is going to give you a matrix. And I'll illustrate that a little bit more with a specific example on the next page. So let's say we write our psi I as equal to this column vector, okay? We got elements A and B. Well, then we would write so this is the ket. We would write the bra part of psi I as equal to, remember, a row vector. The ket is a column vector. The bra is a row vector. So this would be the complex conjugate of this A, and then complex conjugate of B, and then you just transpose it. So, in other words, the bra is the adjoint, or the complex transpose, the conjugate transpose of the ket. The bra is the complex, not complex, conjugate. The conjugate transpose. So adjoint means conjugate transpose. Okay. So now we see if we multiply a bra, let's take two different ones, okay? So I'm going to call this bra psi sub j, and we got psi sub I over here, okay? Let's write psi j was a row vector, so let's call the elements C and D. And then we got psi I here, and we already said that was AB. So this is going to give us a number, because this is the same thing as the dot product. In fact, you can just think of this whole thing as a dot product. So you get CA plus DB, a number. Now, if we turn these around, let's see what we get. So let's take psi I, but the bra side, and then psi j here. Well, now we got a column vector here, and we got a row vector there. And by the rules of matrix multiplication, the matrix you end up with is AC, AD, BC, BD. So you get a matrix. And also, when you take a matrix, let's take a general matrix A and call the elements X, Y, Z, and W. And let's operate with A onto psi I. Well, then it's going to look like this, and you simply perform matrix multiplication, which I'm not going to do here, but you're actually going to end up with another column vector, okay? You're going to have some number here, some number here. And of course, I'm just talking about it in the two-dimensional case. It generalizes to higher dimensional cases. So that's all I wanted to talk about. I hope you found that useful. Thanks for watching, and have a good day.